Okay, welcome. My name's Julian Bunn. I'm a principal computational scientist at Caltech in the Center for Data-Driven Discovery. Today I'm going to be talking about practical genetic algorithms. What are genetic algorithms? I'm going to cover that. I'm going to cover why one might want to use genetic algorithms. I'll cover the genetic algorithm terminology. I'll look at how we build chromosome populations and how we evolve them. I'll look at fitness functions, cost functions, and the way the chromosomes populate and mate and cross over with mutation or not. And then we'll look at a practical example, which is the famous traveling salesman problem, and how we can use genetic algorithms to get solutions for that. Firstly, what are genetic algorithms? They're algorithms that transform themselves to solve problems in ways that are inspired by genetics and natural selection. They were first described by John Holland in Michigan in the 70s, and he was influenced by various other people who'd worked before him. Very much earlier still, Alan Turing had toyed with the idea of evolutionary programs. So the basic concept with a genetic algorithm is to evolve a population of randomly generated algorithms so that they successively improve a solution to a particular problem and achieve a goal. Now, why would you use genetic algorithms? Genetic algorithms are good for finding optimal solutions that are global and avoiding local optimum positions. They're also handy for problems where the variables in your problem may not be continuous. They could be discrete variables, integer variables, string variables, booleans, whatever you might have. They're very suitable for problems where a perfect solution is acceptable. So you're not looking for the solution, but you're looking for a solution which is good. And they're most effective when a good fitness function can be defined. In other words, you can define how well a particular algorithm is performing in your problem. Other examples of this sort of approach are simulated annealing and particle flow. Now, the genetic algorithm terminology is taken from natural selection and genetics. And if we consider natural selection, we know that living organisms are constantly battling nature to survive. The fittest organisms, the strongest, the fastest, the biggest, or the most intelligent, or combinations of those, are the most likely to survive. The surviving organisms mate and reproduce, and their offspring, though they are different, carry the parent's traits which they inherit. The offspring themselves may be fitter or less fit than their parents. The population of these organisms evolves over many generations to have better chances of survival. And that's the principle of genetic algorithms. What actually happens at a biological level, organisms are specified by chromosomes, a genetic code, which is different, or is usually different for each individual. This chromosome, which is a long string of genes, which are instantiated, each gene is instantiated as an allele, has a particular order. And the order and the type of the genes in the chromosome specify it. Now, when organisms mate, their offspring chromosomes are mixtures and crossovers and mutations of the parent chromosomes. So let's look at a representation of a chromosome, which we're going to use a lot in the following slides. What you can see here is a little string of letters, and we term this whole string to be a chromosome. Each of the letters is a position, has a position in the chromosome, and each one of the letters is a particular gene in the chromosome. So this particular chromosome is a list of 9 genes, and each gene has been instantiated as a specific character termed an allele. Now, this particular chromosome is a chromosome which I took out of an example we're going to look at later, which is the path that a travelling salesman would take between cities that are labelled by those characters that you see there. So that's the basic terminology we're going to use. What is a population of chromosomes? Well, it's just a bunch of those chromosomes, typically with lots of different genes clustered together. So this is a group of chromosomes which we're going to use to try and evolve and get a good or better match or fit to our problem space. So this is 6 chromosomes here. In contrast to the previous chromosome that we looked at, this one has binary digits in each of the gene positions. And in fact, much of the early work on genetic algorithms used binary numbers like these for the chromosomes. Now, the way a genetic algorithm works is very similar to the way evolution works, or we believe evolution works. And it's represented by this little flowchart here. At the top, you can see that the first step is to create a population of chromosomes. The next step is to sort the population by fitness, and we'll get into what fitness means in a moment. And then we look to see, after we've sorted them, if the best chromosome in our population matches some stopping criteria, in which case, if it does, then we stop the process. Otherwise, what we do is remove the lower half of the population, in other words, the half of the population which fits most poorly to our goal, and then we mate the upper half, and we'll look at that in detail. And those upper half matings produce offspring. The offspring chromosomes are then mutated, not always, but sometimes. And then we add the offspring to the population, so we have the same number in the population as we started with, and we start the process again. We sort, and then we check if our stopping condition is met. So how do we actually do that in practice? Well, first of all, we need to look at what the problem is that we're trying to solve with a genetic algorithm. Let's take as an example the travelling salesman problem, which, as you probably know, is to find the shortest path between a set of cities where you visit each city only once and you try to minimise the total path length. Once you've defined the problem, then you need to define the representation of the possible solutions to the problem. And in this case, in the travelling salesman case, this is simply an ordered list of cities. So a list of cities in which the salesman should visit. Then we need to define the fitness or the cost function. That is how the chromosomes which we create will evaluate each of their respective solutions. So in the case of a travelling salesman, we just look at the total length that's specified by the path in the chromosome, by the ordered city list. Then we define what are called genetic operators, and this is really how the chromosomes will initially be created, and how they will mate, and how they will then mutate. And then, as we looked at before in the flowchart, we decide on the stopping conditions. These are when the algorithm should stop. Of course, we can let the algorithm run forever, and it can produce many hundreds and thousands of solutions, but at some point we need to decide whether we've found the solution we're looking for, or whether the solution that's been found so far is good enough, or whether some error term has been minimised. And then we write the code after we've decided all that, or if you don't like writing code, then you can use somebody else's code. So let's look at this travelling salesman problem in a little bit more detail. The salesman, he wants to sell his wares in all the cities in a region. If you look at the diagram on the right, there's a set of cities there which are rather artificially placed in a spiral orientation. And you can see the cities are labelled by A through J. The salesman wants to minimise the amount of time he spends on the road, and so he likes to try and find the shortest path between those cities, what order he needs to travel that path in. So we've got these 10 hypothetical cities, and if you look at the number of possible paths, then it's 10 factorial, which is just over 3.5 million possible solutions. Now, of course, if you've got a large computer, you could probably look at each one of those, but that's not a very elegant way of doing it. It does seem intuitive when you look at this diagram, and why I chose this spiral, that the shortest paths are in fact going A, B, C, D, E, F, G, H, I, J, or in the reverse order. So we'd expect our genetic algorithm to come to that solution. So for this particular problem, we create a population of chromosomes, and the chromosome will just look like a list, an ordered list of cities. And here's a little bit of Python code which does this. Of course, you don't have to use Python. You can use anything you like. But this is part of a code which is available for download that supports this lecture, which you can look at and find bugs in if you want. Here we have a little bit of code which basically makes a random shuffle of the ordered of the cities, so A through J, and it creates a chromosome with that randomly shuffled set. And it keeps on doing that until it's got the number of chromosomes we want in our population. And we'll talk a little bit in some further slides about how many chromosomes we want to generate like that. Now, defining the fitness function, we already said that the best fitness, the best chromosome will have the shortest path. And so this little bit of code here does a very simple thing. All it does is it looks for this particular chromosome, it looks at all the cities in the list, and it computes the distance between each of them in order, and it sums the path travelled. So in general, deciding on a good fitness function is really the main key to success with genetic algorithms, as we'll see a bit later on. This seems like a good fitness function, at least to me. Now we've got our list of chromosomes, our set of chromosomes. We need to order them, first of all, by fitness, because we've generated them randomly. It could be that one of the chromosomes actually specifies the order that we're expecting, which is A through J in order. But normally it doesn't, particularly since there's a lot of possible solutions. So conventionally, after we order the chromosomes in our population, we discard the bottom half. We don't need to do that, but that's conventionally what is done. And then the top half of the population will become what is called the mating population. So the best chromosomes are going to be used to mate with one another and hopefully produce offspring, some of which are even better than the parents in the mating population. So we pick pairs of chromosomes at random. And then with each mating pair, we create a new pair of chromosome offsprings from those parents. We don't need to create a pair, but it just turns out that it's convenient and it's elegant to create two from one parent. You could equally create one, or you could create three or more from each set of parents. After we've created the offspring, we may mutate each one of them, and we decide whether to mutate the offspring by picking a random number. And that random number decides whether or not the offspring chromosome will be mutated. Typically, we run probabilities of that happening of around 50% to 25%, something like that. After we've done that, then we add the offspring to the offspring population, and then once we have enough offspring in the offspring population to make up our original population size, we add them all in. So let's look at how the mating procedure actually works in the genetic algorithm. And there's a couple of ways, at least, of doing it. The most common one is what's called single-point crossover. And this is where a piece of the mother chromosome is swapped by the same section in the father chromosome. And so the two offsprings take pieces from the father and pieces from the mother. And so you can see here that the mother begins BAFH, and offspring 1 has the same beginning, that the end of its chromosome corresponds to the father's end, and vice versa for the other offspring. So that's one way of mating the chromosomes. Another way is a double point crossover, and that's pretty much self-evident from the name. Here you just take a segment out of each of the mother and father chromosomes and you swap the segments between them. So you get an offspring that has the mother's segment and the other offspring has the father's segment in the crossover slice, as illustrated. Now, in the case of some problems, and in particular the travelling salesman problem, we need special crossover methods, because if we did what was on the previous slide with the city list, then we'd end up with duplicate cities which violate our conditions for a solution. This is illustrated here. If we take a mother and a father chromosome and we do this, we take a slice out of the middle, and if we look at the first preliminary offspring, you'll see that the red circles show where we now have duplicates in our list, in our chromosome. That's no good, because we can't have duplicates. The problem dictates that we can't have them. So the way of correcting for that, and this isn't the only way of doing it, is just to look at which chromosomes, which genes are missing, which alleles in particular are missing, and replace them in order in the corrected offspring. So this is a little bit ad hoc, but a lot of what you do in genetic algorithms is ad hoc. Now we'll look at mutation, and this is a process where once we've got the offspring, we decide whether or not they're going to survive as they sort of came out of the womb, if you like, or if they're going to actually undergo some sort of genetic mutation. There's some probability associated with that, as we said before. The idea of a mutation is it helps to diversify the population. And it's achieved just by making some sort of a random change to the chromosome. So here's a typical set of methods that you might use. If you pick a random gene, a random allele in the chromosome, and just change it to a different one. Just change it to a different value. You can swap two alleles in the chromosome, so you just exchange the positions of those two alleles. You could also cut the chromosome at a random position and then just take the head and put it in front of, take the tail and put it in front of the head. And I'm sure there are many other ways of mutating that you can probably think of. Now we've defined what the operators are that we're going to use with our genetic algorithm, with our chromosomes, and we now actually want to run the algorithm. So as we saw before, at each epoch, which is each new generation of chromosomes, we order all the chromosomes by fitness, and then we decide whether or not to continue to the next epoch. And we do that by saying, well, is the best chromosome meeting our stopping criteria? If so, when we finish. If we've met the number of epochs which we're allowing the genetic algorithm to run for, then we finish. Or if we find that there's no improvement from the previous epoch or a succession of many previous epochs in the best chromosome, we're going to have to say, well, we give up at this point and finish. So a lot of these parameters which are used when running the algorithm are rather ad hoc and heuristic. The size of the population, for starters, the probability of mutation occurring, the size of the crossover pieces between the chromosomes, and the stopping criteria. You typically derive those heuristically. Now, some people have come up with rules of thumb. This is one I saw quoted, that the chromosome population size should be greater than 4 times the chromosome length. Now, in my experience, you need much bigger chromosome population sizes than that, but maybe you can get away with it for simpler problems. Now, here's another bit of code. This is a piece of code which is an example of how you might mate chromosomes, and we already looked at how that's done by swapping the pieces of the father and mother chromosome. And in Python, at least, there are some very nice list operators which you can use to make this rather easy to write the code for. In Java, there are similar functions as well. I wouldn't like to do this in Fortran, but you probably could. This, again, is part of the example code that you can download and play around with. This is an enhancement of the previous slide's code, but here we're trying to avoid this duplication, which we mentioned a couple of slides ago, which is where we need to preserve the fact that in the case of a travelling salesman problem, we only have city A, for example, appearing once in the list. And so this is the code which ensures that if there are any alleles missing out of the offspring, then they're replaced with the duplicated alleles in that chromosome. This little piece of code just shows you how this is done in Python. So this is, again, we're seeing here some nice elements in the Python where you can look at this set function, which allows you to look whether the chromosome which you've generated and the set of alleles in that chromosome and the set of alleles in the target, if there's anything missing. That's a convenient way of dealing with this problem. So now we have our population of chromosomes, we have our fitness function, we know how to mate the chromosomes, we know how to mutate them, and when we run the algorithm, typically we want to see how the algorithm is performing, and there are various ways you can see how the algorithm performs as it generates new populations. The most visually appealing one, of course, in the travelling salesman problem is to look at the order of the cities which the genetic algorithm says are the best ones to minimise the travel distance. And you can see that in this slide we've got a diagram of the best chromosome in an initial population of 20 chromosomes. These are 20 chromosomes which are generated completely at random. And in this particular population, the best chromosome is showing a really rather silly path through the cities. Now, if we run our genetic algorithm over many epochs, then at epoch 100 for this particular set of chromosomes, you can see there's some considerable improvement in that the path is obviously approaching a minimum, but there's still a problem because it's making a step between A and J, which it shouldn't make a step. Now, faced with this, it's of course easy then to just increase the population size or to let the population or let the genetic algorithm run for longer. If you increase the population size to 100 in this case, then after a while, after the same number of epochs, you find that the genetic algorithm converges on a good solution. It's probably the good solution, but I don't think you can say that for certainty. So when we're running genetic algorithms in general, you have to make some judgment calls about what is a good solution and what is a bad solution. You really have to look at the way the genetic algorithm behaves and adjust the parameters accordingly. And that brings us back to the fitness functions, which is the most important part of designing a genetic algorithm. You need to be sure that you've got a good fitness function, because with a good fitness function, the genetic algorithm will converge more rapidly on a globally optimum and desired solution. If you have a poor fitness function, then many things can happen. The genetic algorithm may never converge, or it can converge to a local optimum, or it converge to a solution which is to a different problem than the one you're intending, or it will take too long to run, or it can start discarding good chromosomes which would actually have been a good solution to your problem from the population while it's evolving them. So in some cases, the genetic algorithm travelling salesman problem is a very simple problem, but in some cases the fitness function may need to be quite complicated. If the fitness needs to be expressed in terms of a cost, So you can think with the travelling salesman problem that the cost of a path is the length of the path. So we're trying to minimise that. But you could just take 1 over the length of the path as the fitness, or you could take minus the length of the path as the fitness, if that's the sort of expression you have for the solution. Another opportunity which you have with genetic algorithms is that when you're doing the fitness function evaluations on each of the chromosomes individually, this is a very nice opportunity to parallelize your algorithm. So you can allocate a set of cores to each chromosome to one of a set of cores, and then have these fitness functions, which generally tend to be the most compute-intensive part of the algorithm, executing in parallel. And it may be harder than it first appears to define a good fitness function. So that finishes up genetic algorithms, this practical introduction. Some of the applications, some more famous applications of genetic algorithms are in timetable optimization, electronic circuit reverse engineering. So this is where you have some measurements on an unknown circuit and you want to understand how the electric components are connected in the circuit and what types of components there are. There have been applications of genetic algorithms to code breaking. So if, for example, you have a simple alphabetic substitution cipher, then you can use a genetic algorithm to find what sort of substitutions match that with the aid of a dictionary and a suitable fitness function. Another application is finding good initial weights for a neural network. In neural networks, we start the network off with a set of weights and biases. Typically, it takes a long time to train the neural network so that the weights are good. But with a genetic algorithm, you can make a nice first approximation of the best weights in the neural network. And one of the students I worked with here at Caltech had a very nice application of genetic algorithms where he was generating art. And the way he was doing that was he was taking a piece of art by, in this case, he was looking at Mondrian, and he was devising a genetic algorithm which would try to replicate as closely as possible the artwork. And the way it was doing that, it was a graphics program which was being evolved as successive epochs went on. And then there was a similarity metric between the evolved images which the graphics program was generating and the piece of art which he was trying to emulate. Some of his results were really quite striking. There are several genetic algorithm toolkits that you can use. MATLAB has a thing called the Global Optimization Toolbox. There's a thing called DEEP. There's a thing called PyEvolve. And you can also download the code for this. In general, genetic algorithms, if you know how to program or you're handy with programming, they're rather easy to write yourself. There's no real need to take on board an enormous package if you don't really need to. An enhancement of genetic algorithms is what is called gene expression programming. If you want to explore further in genetic algorithms, this is where the chromosomes actually include symbolic expressions in the variables in your problem space. And there are some very interesting results with gene expression programming which have been applied to large scientific data sets where it's known that the variables can be expressed symbolically. Well, thank you very much for paying attention, and that's the end of the genetic algorithm lecture.